Hi, I'm Raymond Lin, and this is Strategic Math. So we have come to our 7th lecture. In our 7th lecture, we're going to talk about we solve things with grids. So today's topic is actually quite interesting. We're going to talk about a special way to solve many kinds of problems that are common in permutations and combinations. So we'll first talk about what we'll talk about today, and we'll get a quick go through of it. First, that we'll talk about how we'll count in grids. And to talk about this, we'll talk about shortcut problems. Then we'll talk about Catalan numbers. And then we'll use Catalan numbers to solve problems like lead all the way problems, queuing problems, and lastly, we'll talk about how we'll solve games with grids. So first, let's talk about shortcut problems. So it asks for how many ways are there to walk from A to B with the shortest route. So to answer this question, we'll first have to talk about what will happen if we walk to the shortest route. So if we want to walk with the shortest route, this means that there's no going back from A to B. So if we need to walk from A to B, no matter how the route will look like, we'll always walk 6 times to the right and 4 times up. Only this way we'll get from A to B. So if we want to ask for how many ways, that means we'll have to construct different kinds of routes. So to construct different kinds of routes, we'll use 6 right arrows and 4 up arrows. So this is actually just the same permutation of the same objects. This means that the answer for this problem is 10 factorial divided by 6 factorial times 4 factorials equals to 2000 and equals to 210. So this is how we solve the shortcut problems. So let us now look at a further problem based on this one. It asks for the shortest route to walk from A to C to B. So in this problem, it says that we need to go through the point C. So we can just separate this problem into 2 parts. From the problem where we get the shortest route from A to C, and the problem of the shortest route from C to B. So this means that the answer for this question is actually quite simple, which is just 90. After we've talked about shortcut problems, we'll next talk about Catalan numbers. So Catalan numbers is actually talking about the number of paths from A to B, which is the bottom left corner and the upper right corner, without going across this diagonal line. So what this means is that we can walk a route like this. So I'll draw a route like this. So this route will be valid because this route doesn't go across the diagonal line, while this route will not be valid because in this route from A to B, we go across the diagonal line. So you can also see this by using pictures from Wikipedia. So in this picture, it draws all kinds of the possible routes in different scenarios, like a square with an edge of 1, 2, 3, and 4. So the way we count how many paths are there is by using this function. The Catalan number Cn will be equal to 1 over n plus 1 times the combination of n from 2n. So this is a function where we generate Catalan numbers. In this video, we'll not talk about how this function is formed, and we'll list out Catalan numbers from 0 and 7. So remember the formula for us to generate Catalan numbers, and the proof is not actually quite important. But if you want to know more about the proof, I'll put the links of the proof below in the description box, and you can watch it on your own. So let's now talk about how we'll use Catalan numbers to solve problems. The first problem we're going to talk about is lead all the way problems. The problem is like this. Amelia and Betty are two candidates for the president of Candy Club. There's a total of 14 voters. After the votes are counted, Amelia has 8 votes and Betty has 6 votes. If throughout the counting process Amelia always has more votes than Betty, then how many possible processes are there? So there's actually a leap from this problem to Catalan numbers. And the way we solve this problem is that we need to use grids. So how will we apply grids? Well, we can see that every move to the right and every move up can be counted as a vote. And we already know that at the end, Amelia will get 8 votes and Betty gets 6 votes. This means that this grid will be an 8 times 6 grid. We let that going right means that Amelia gets a vote and getting up means that Betty gets a vote. So all of the possible ways from A to B, there's another condition that we need to consider is that Amelia must always be greater than Betty. This means that we can draw a diagonal line like this, because Amelia and Betty cannot have the same number of votes, so 1-1 cannot be possible, and 2-2 can also not be possible. So the only valid point will be 2-1. So by considering all the valid points, we can draw out the diagonal line, and the path from A to B cannot go across this diagonal line, or the path needs to stay below this line. So if we solve this problem by counting, we can get the answer 429. But there's another way we have talked about, that is to use Catalan numbers. So if we want to use Catalan numbers, we have to create a grid. So create a grid to create a square will extend the diagonal line and form another little new square. So we can see that this square will be a square with a length of 7. This means that we'll just solve for the Catalan number of 7, which is 429. Because we know that from this point to this point, it has the same number of ways of roots. This means that the points we're asking for will also be 429. And this is how we get the answer for this question. Next, we'll still talk about this problem, but with a little twist. This time, there's a total of 15 voters, and Amelia has 9 votes at the end. So we'll use the same logic and apply the grid to this problem. This time, we have a length of 9 and a length of 6. So we'll again use the neat trick we've already talked about and use Catalan numbers to solve these problems. But this time we've generated a grid that's 8 times 8, and we have generated 3 more little squares. So to solve for this point, we already know that this point is CA and this point is C7. This point is also CA and this point is also C7. So by using the functions that we've memorized, we can easily get that the answer for this question is 1001. And this is how we use Catalan numbers to solve these kinds of lead all the way problems. Next, let's talk about queuing problems. So the queuing problem is like this. 8 kids with different heights are lining up in 2 rows. The kids in the first row must be shorter than the one in the second row, while in each row the kids must be lined up in ascending heights. How many ways are there of lining up? So this question needs a bit of imagination. So first, because the kids are with different heights, we'll number the kids. The kids with the lowest height will be 1, and the kids that is the highest will be 8. So we'll draw out the rows. So you can easily see that 1 must be on the bottom left corner and 8 must be on the upper right corner for us to fulfill the condition. So how will we change this problem into grids? So the most important thing here is that how we will put the kids. So the kids from 2 to 7, we can't just put them in there without any logic behind them. So the simplest way for us to put 2 to 7 is that we'll put them in order. We'll first consider where we can put 2, and then consider where we'll put 3, and then so on. So the place we can put 2 is either the red star here or the black star there. So there are 2 places for us to put 2. And notice that if we put 2 on the black star, this means that the next number 3 must be on the red star so that we can fulfill the condition. So this is actually somewhat like the diagonal line that we have already drawn many times on grids. So let us let that if we put a number on the lower row, it will be a move to the right, while putting a number on the upper row will be a move to up. So we'll draw the diagonal line. The diagonal line will be here, and we can easily find that the answer for this question will be 5. So lastly, we'll get a bit away from Catalan numbers and we'll talk about how we will use this concept to play games. So the game starts with s equals to 0 and let the coin be fair. In each round, if we flip a head, then s will increase by 1. If we flip a tail, then s will decrease by 1. At the end of the game ends either when s equals to 3, which means that you'll get 3 points, or 7 rounds have passed. So how many possible processes are there? So if we want to put a game onto a grid, we have to think about some things. Like if we want to put something onto a grid, this means that going right will mean something, like on the case about queuing problems, going right means that we are putting a number on the lower row. And going up also needs to resemble something. And lastly, we'll talk about a diagonal line. That means there's a condition that we need to fulfill and we cannot go across that condition. So we'll first identify the conditions and the different statements that we've talked about in this scenario. So it might be easy to see that if we want to choose one thing as going right or going up, it will be s. If s plus 1, this means that we're going right. And if s minus 1, this means that we're going up. So because there must be only 7 rounds, this means that the number of going right plus the number of going up needs to be equal to 7. So the 0.07 will be valid and the 0.16 will be valid, but the 0.17 will not be valid. So we'll draw the diagonal line. Next, we'll look at the other condition where s equals to 3. So when s equals to 3, the game stops. This means that the number of arrows going right minus the number of arrows going up must be equal to 3. And this is a condition where we stop. So you can easily see that the points that fulfill will be the points 3, 0, 4, 1, and 5, 2. We can draw the other diagonal line. Then you need to know one thing, because when we get to the point 3, 0 and when we get to the point 4, 1, this is the end of the game. So we cannot go up. So the path going up will not be valid. So after all these kinds of thinking, and we can make sure that this whole logic of bringing a game onto a grid is valid, we can erase all of the lines that we do not need. And this is what we'll solve for the path. So the path for this graph is actually quite simple for us to solve, because you only need to add numbers. Like on this point it is 1, so there's only one way going to this point and one way, and this is 1, while 1, 2, 3 and 4, and this point will be 4. So to solve this grid, it's actually quite simple, and we can add all the possible outcomes for us to get the answer, because this question asks for all of the possible ways for the game to end. So we'll add these numbers. We'll add 1, 7, 21, 34, 28, 9, 3, and 1. And at the end, we'll get our answer, which is 104. So in this example, we've learned how to get a question into a grid, how to reshape the question, and then use our logic of creating conditions with diagonal lines and representing going right and going up with another meaning. Using this way, we can solve questions much more clearer and easier. And this is the end of our 7th lecture. We'll see you soon on our lecture 8, where we'll talk about geometry, special angles.